A small, unventilated room, an open fire burning in the center. In the modern world, this is not a home. It is a death trap. Deadly, odorless carbon monoxide would quickly fill the space, displacing oxygen. Smoke inhalation would sear the lungs. Within hours, anyone inside would be unconscious, or worse. And yet, for millennia, this was the central reality for indigenous peoples across North America. From the frozen Arctic to the Great Plains, survival depended on fire, and fire was brought indoors. This creates a fundamental paradox. How did they live, cook, and sleep in small shelters, often packed with people, surrounding an open flame without suffocating? How did they master a force that, by all modern logic, should have killed them in their sleep? The answer is not magic, it is engineering. We have been taught to see these structures through a lens of simplicity, as primitive huts or simple tents. This assumption is wrong. It masks the truth of what these dwellings truly were. Sophisticated, high-performance engines, precision-tuned to manage the physics of fire. The peoples who built them were not just occupants. They were masters of fluid dynamics. They understood, intimately, that heat rises, cold air falls, and that survival lies in precisely how and where those two forces are allowed to meet. The challenges were immense. It was not just about warmth. An effective shelter had to solve multiple, competing problems simultaneously. It had to trap radiant heat to keep bodies warm, but it also had to exhaust the toxic byproducts of combustion. It had to create a livable indoor microclimate while withstanding the massive external forces of the macroclimate, be it an Arctic blizzard or a prairie gale. Simply punching a hole in the roof is not a solution. A simple hole lets all the precious heat escape. On a windy day, it can create a downdraft, pushing a plume of toxic smoke back down onto the occupants. A simple opening doesn't solve the problem of oxygen. A fire consumes air. It needs a constant, fresh supply. If that supply isn't managed, the fire will die, or the occupants will. Historians and engineers are now re-examining these structures, not as cultural artifacts, but as feats of applied science. They are discovering that the shape of the structure, the materials used, and even the interior decorations were all critical components of a complex ventilation system. To understand this lost science, we must first abandon the image of the smoky hut. We must instead learn to see the teepee, the igloo, and the wigwam as they were, breathing, living machines. Our first case study begins on the Great Plains, with a structure that seems impossibly simple, yet hides one of the most brilliant solutions to the problem of air: the Lakota teepee. To the untrained eye, it is the simplest of structures. A cone of animal hides draped over a fan of wooden poles. The Lakota teepee, or teepee, is an icon of the American plains, but its iconic status masks its technical brilliance. This structure was not a mere tent. It was a portable, high-performance survival machine, engineered to perfection for one of the most extreme climates on Earth. The Great Plains were a land of relentless wind, brutal winters, and sudden, violent storms. A shelter here had to be anchored against gales, insulated against sub-zero cold, and portable enough to move with the bison herds. The teepee's conical shape was the first stroke of genius. It is inherently aerodynamic, presenting a minimal profile to the wind, allowing gusts to flow around it rather than tear it down. But its true innovation was internal. Inside, a fire was essential for life. The most visible feature is the opening at the apex, but this was far from a simple hole. It was a dynamic vent, controlled by two large, pole-mounted flaps, the ears of the teepee. These were not decorations. They were the engine's throttle and steering. By adjusting the flaps, the occupants could shield the opening from wind, preventing catastrophic downdrafts of smoke. They could also use the prevailing wind, angling the flaps to create a low-pressure zone that actively pulled smoke out of the dwelling. This solved exhaust, but it did not solve the problem of oxygen. A fire consumes air, and a simple draft along the cold floor would freeze the occupants. The solution was the teepee's hidden masterpiece, a second inner wall. This was a lining, often of hide or canvas, that stretched around the interior, but it did not reach the ground. This gap, just a few inches, was the secret. Cold, fresh air from the outside was drawn in under the main, outer cover. But instead of spilling across the floor, this cold air hit the inner lining. The lining acted as a baffle, directing this fresh air upward into the narrow channel between the two walls. This created a perfect convection engine. The fire, burning in the center, drew its oxygen from this channel. The fresh air was pre-warmed as it rose between the linings, feeding the base of the fire for a hotter, cleaner, and more efficient burn. The hot, toxic smoke rose straight up and was expelled through the precisely controlled smoke flaps. The result was a near-perfect microclimate. The occupants were protected in a bubble of radiant heat, insulated from the cold outer wall by a circulating current of air. They were never touched by a cold draft, nor choked by smoke. While scholars still discuss the precise evolution of this design, its effectiveness is undeniable. The teepee was not a hut. It was a breathing machine, a thermos, and a chimney, all in one. But what if the environment was even colder? What if the only building material was frozen water? In the extreme, frozen expanse of the Arctic, the engineering challenge was absolute. There was no wood, no hide-covered plains. The only abundant building material was the ground itself, snow. The Inuit solution was the igloo, a structure that defies modern intuition. It is a house built of frozen water, yet warmed by an open flame. This is the ultimate paradox. How could a fire burn inside an ice dome without melting it? And, crucially, in a structure designed to be airtight, how did the occupants breathe? First, the material itself is misunderstood. The igloo was not built from ice. It was built from hard-packed, wind-blasted snow. The strength came from the interlocking, spiral-cut blocks, forming a catenary dome, the strongest self-supporting shape in architecture. But its thermal genius lay in the snow's composition. Snow is not a conductor. It is one of the world's greatest insulators. Its structure is up to 90% trapped air. This air, held in tiny pockets, formed a thick thermal barrier. The heat source was not a roaring wood fire. It was the kulik, the traditional Inuit lamp. Carved from soapstone, this wide, shallow lamp burned rendered sea mammal blubber with a moss wick. It provided a low, steady, and incredibly efficient source of both light and, critically, radiant heat. This heat immediately began a process of transformation. The internal temperature would rise dramatically, often 20 to 70 degrees Fahrenheit warmer than the outside. The inner surface of the snow blocks would begin to melt. This melt, however, would refreeze into a thin, solid glaze of ice. This glaze sealed the structure, making it windproof, and simultaneously reflected the lamp's radiant heat back onto the occupants. But this airtight seal created the suffocation problem. The solution was a masterpiece of understanding air density. The igloo was not just a dome, it was a multi-level system. The entrance was a low tunnel, and the living platform inside was elevated. The floor of the igloo, at the base of the entrance, was the lowest point. This was the cold sink. The physics were flawless. As the kulik burned, it consumed oxygen and produced carbon dioxide. CO2 is heavier than oxygen. This heavy, toxic, and cold air would sink, flowing off the sleeping platform and pouring down into the cold sink near the door, where it was trapped. A tiny vent hole, often just a few inches wide, was cut near the top of the dome. This was the exhaust. The hot, lighter air, along with water vapor and carbon monoxide, rose and exited. This created a gentle, chimney-like draft. Fresh, oxygen-rich air was pulled in through the low entrance, flowed across the cold sink, and was warmed by the lamp, rising to the living area. The igloo was a three-part stratified system: a trap for cold, toxic air at the bottom, a warm, oxygen-rich living space in the middle, and a vent for hot exhaust at the top. The Inuit did not just build a shelter, they built a machine that manufactured a livable atmosphere. But this engineering was not limited to snow. In the woodlands of the East, a different set of materials would yield an equally brilliant solution. From the frozen Arctic, we travel south and east into the vast, dense forests of the woodlands. Here, the climate presented a different, more insidious enemy. It was not the dry, extreme cold of the plains or the pole. It was the damp. In the eastern woodlands, the air is heavy with moisture. Rain is frequent, and the ground is soft. For the Algonquian-speaking peoples, a shelter made of animal hide, like the teepee, would be a disaster. It would quickly absorb moisture, grow heavy, and rot. A shelter of snow was impossible. Their solution was the wigwam, or wetu. Like the teepee, the wigwam is often misunderstood as a simple hut. It was anything but. Its construction was a marvel of resourcefulness, using a flexible framework of bent saplings driven into the ground and lashed together to form a sturdy dome. This dome shape was incredibly strong, shedding rain and snow with ease. But its genius, once again, lay in its skin. The wigwam was a multi-layered system, engineered to do something the teepee and igloo did not have to: manage liquid water. The outer layer was the armor. It was typically made from large sheets of bark, often from birch, elm, or cedar. Birch bark, in particular, is a natural high-tech material. It is rich in suberin, a waxy, waterproof substance that makes it impervious to water and resistant to rot. These bark shingles were overlapped, creating a weatherproof shell. In other areas, thick, tightly woven mats of cattail or bulrush were used. When these mats got wet, their fibers would swell, tightening the weave and making the entire surface watertight. This solved the problem of rain, but it did not solve the problem of humidity. Inside, the occupants were breathing, cooking, and drying wet clothes. This all released a tremendous amount of moisture into the air. In a simple, sealed shelter, this moisture would condense on the cold inner walls, dripping on the occupants, ruining supplies, and creating a miserably damp, cold environment. The solution was the wigwam's second layer, an inner wall of woven mats, often more delicate and breathable than the outer ones. This lining created that familiar, critical air gap. Here is how the system worked. Warm, moist air from the occupants would rise and pass through the breathable inner lining. It would then enter the air gap, where it met the cold, waterproof outer bark. The moisture would instantly condense, but it did so on the inside of the outer wall, safely outside the living space. This liquid water would trickle down the bark and be absorbed into the ground, leaving the inner mats, the bedding, and the occupants perfectly dry. The fire was managed in a similar, sophisticated way. A central hearth held the fire. At the apex of the dome, a smoke hole was left open. This vent was not complex like the teepees, but it was often covered by a movable piece of bark or hide that could be adjusted with a long pole, acting as a simple chimney cap to block rain. The wigwam was, in effect, a double-walled, breathable, waterproof dome. It was a shelter that managed not just air temperature, but the entire hydrological cycle. It was a home engineered to stay dry, even when the world outside was soaking wet. The Lakota teepee, the Inuit igloo, the Algonquian wigwam. 3 structures, separated by thousands of miles, built from entirely different materials, in vastly different climates. A cone of hide, a dome of snow, a dome of bark. Yet, when we dissect their designs, we find an astonishing, shared engineering DNA. Each structure solved the suffocation paradox. Each one was a sophisticated machine for managing airflow, heat, and human life. The teepee, with its 2-layer lining, was a convection engine, preheating its own oxygen supply. The igloo was a stratified system, using the density of air itself to create a cold sink for toxic CO2 while sealing in radiant heat. The wigwam was a hydrological manager, a double-walled dome that breathed, purging moisture to the outside. Each design, in its own way, mastered the air gap. This was the fundamental principle. Whether it was the space between the teepee's linings, the trapped air in the snow blocks of the igloo, or the gap between the wigwam's inner and outer mats, this feature was the key. It allowed for a separation of functions, an inner layer for comfort and an outer layer for protection, with a workspace in between for the physics of air and water to operate. This parallel evolution is not a coincidence. It is the signature of true science. It proves that for millennia, indigenous peoples were not just surviving in their environments, they were studying them. They were applied physicists, fluid dynamicists, and engineers of the highest order. Their laboratory was the natural world, and their experiments were conducted over generations, with survival as the ultimate peer review. This is the knowledge that was lost, or more accurately, dismissed. The label of primitive was a convenient fiction, one that allowed a colonial mindset to overlook and therefore devalue the profound technical achievements of these cultures. Scholars today, using computational fluid dynamics and thermal modeling, are only just beginning to quantify what indigenous builders knew by heart. They are finding that these structures are not just effective, but in many cases, optimal. This comparison reveals our core thesis. The question was never, how did they survive in those smoky huts? The real question is, how did we become so blind to their genius? The suffocation paradox was never a paradox at all. It was a failure of our own perception. The Lakota teepee, the Inuit igloo, and the Algonquian wigwam were not huts. They were precision-engineered solutions, the result of a scientific process honed over 1,000 generations. They stand as a powerful testament to a different kind of knowledge, one based not on conquering nature, but on deep observation and cooperation with its fundamental laws. They are a profound lesson in ingenuity, proving that sustainable, brilliant design is not born from complex technology, but from a deep and respectful understanding of the world. It is a science of survival we have not just forgotten. It is one we are only just beginning to appreciate.